Every time you run git push, your laptop proves who you are to GitHub in about a tenth of a second. It sends no password. It sends your private key across the internet exactly 0 times. And here's the part most engineers get wrong. There is no random challenge for you to sign either. That last one is the myth we are going to break today, because once you see what's actually being signed, this whole thing finally makes sense. Stop and notice how weird this actually is. When you clone over HTTPS, GitHub makes you paste a personal access token. When you clone over SSH, it asks you for nothing at all. Same push, same repo, same servers, but one of them somehow already trusts your machine. Something on your machine is silently vouching for you and it is not a password. That something is a pair of cryptographic keys. SSH authentication is built on asymmetric cryptography. You have two keys that are mathematically bound together. The private key produces a signature that only the matching public key can verify. And crucially, being able to verify a signature tells you nothing about how to forge one. The public key can check the math, but it can't run it backwards to recover the private key. So the public half is safe to hand out to the entire world, and the private half never has to leave your laptop to prove that it exists. That single asymmetry is the entire trick. On disk, that key pair is just two small files, usually living in your .ssh directory. IDRSA is the private key, a few kilobytes, and the one secret you actually have to protect. IDRSA.pub is the public key, only a few hundred bytes, and it is safe to paste anywhere. That size gap is a good instinct. The private key carries the full math, the public key is a compact fingerprint of it. SSH is so paranoid about the private key that it refuses to use it if the file permissions are too open. That is the chmod 600 you have probably copy pasted a dozen times without knowing why. It is SSH making sure no other user on the box can even read your private key. Now, here is a step almost everyone skips over mentally. Before any of this works, your public key has to already be sitting on the server. On a raw Linux box, that means it is listed in the server's .ssh authorized keys file. On GitHub, that means you pasted it into your account's SSH key settings. This is a one-time setup step done long before today's push. And this is exactly where the biggest misconception lives. The server does not receive and then store your public key during login. It already had it, and during authentication, it only looks it up. If your key is not in that list beforehand, the handshake fails, no exceptions. Quick one before the main event. If this is already clarifying something you've typed 100 times, drop a like. It's the single biggest thing that helps the channel grow. Okay, now the part I promise, the actual handshake. Here is what actually happens when you authenticate over SSH. Step 0, and this is the part people miss. Before authentication even begins, the client and server have already built an encrypted channel. They did that with a Diffie-Hellman key exchange, which produces a shared secret that neither side ever transmitted. That same exchange also produces a unique session ID for this one specific connection. Hold on to that session ID because it is the hero of this entire story. Step 1, the client offers its public key and asks, in effect, would you accept this one? Step 2, the server checks that public key against its authorized keys list. If it is not there, everything stops right here. If it is, the server says go ahead and prove you actually own it. Step 3, and this is the myth buster, the client does not wait for a random challenge from the server. Instead, it takes that session ID from the Diffie-Hellman exchange, bundles it with a few connection details, and signs that blob with a private key. Step 4, the server verifies the signature using the public key it just looked up. If the signature checks out, you're in. The obvious question is why there is no classic server sends a random number challenge step. The answer is that the session ID already does that job for you. It is unique to this one connection derived from fresh Diffie-Hellman values that change every single time. So a signature over that session ID is completely worthless on any other connection. An attacker who records your signed blob can't replay it because the next session has totally different ID. The freshness that a challenge normally provides is already baked into the encrypted channel you are sitting inside. That is the elegant part. SSH reuses work it already did instead of adding a redundant extra round trip. Put the whole path together and it reads as shared secret, look up the key, sign the session ID, verify the signature. So let's connect all of this back to the command you actually type. When you run git push over SSH, git itself does none of this crypto. It quietly shells out to your system's SSH client and hands off the connection. SSH reads your private key from .ssh IDRSA. It runs the exact handshake we just walked through against GitHub servers. GitHub validates your key, but notice that it is really validating two different things. First, authentication. Are you really the person who owns this key? Second, authorization. Does that person actually have right access to this particular repo? Passing the crypto does not grant you the push, you still need permission on that repository. Once both checks pass, your commits go up and you never saw a single password prompt. Step back and you can see exactly why the industry moved to this. A password has to travel to the server to be checked at least once. A private key never moves. Only signatures made with it do, and those are useless to steal. If GitHub's database leaked tomorrow, it would expose everyone's public keys, which are already public by design. Your actual secret never sat on their servers in the first place. That is why key-based auth is both more convenient and dramatically harder to phish. A couple of practical things now that the model is clear. You can put a passphrase on the private key itself, so the file is useless even if someone copies it. SSH-agent then holds the decrypted key in memory, so you're not retyping that passphrase all day. And if you are generating a new key today, prefer this one over old RSA, smaller, faster, and more modern. So the next time git push just works, you will know exactly what happened in the 10th of a second. No password crossed the wire, no challenge was ever sent, and your private key never left your machine. It just signed one unique number and let the math speak for itself. If this made SSH finally click, subscribe. I'll see you in the next one. Thank you.